First of all, thank you everyone for coming, and I really appreciate especially the guests who came from far away and the guests who came from, and the speakers who are already here for participating in this day. I found it very interesting and enjoyable, and I hope everybody else did too. When Orna said that I could have 25 minutes, I said, well, we'll call the talk Summing Up. The question is, what do I want to sum up? You could say, I'm retiring, or talk about, my entire life, etc. I don't think so. Not in 25 minutes, so I'm not going to do that. Also, even my personal history, well, there was 10 minutes on it in the morning, so that's mainly what I'll say about that. To talk about what I've done in the Technion and my service activities, I'll give that 2 slides. But what I really want to talk about is my research, what I've done over the years and why I've done it, and the agenda that I have that I think some of the other people who have spoken here and also some of the other people in this room are also could and have bought into some of this agenda, and so we'll see if you find these things relevant. So as far as what I've done over the years, in the 30-something years I've been in the Technion, I've taught well over 90 courses, distinct lectures and seminars and whatever. The main courses that I taught for years at a time were data structures, compilation, programming languages, and 2 courses that I helped to develop, software engineering methods and formal specifications. I put a lot into it, and I enjoy doing it, and I have a lot of good students. As far as supervising students, I had 9 PhDs and somewhere around 25 master's students, where a master's student in the Technion, as the ones from the Technion know, is half a PhD at least, and it very often comes out to be a journal paper, etc. So I've worked together with a lot of really good, nice people. Overall, I've written somewhere around 100 journal and conference papers. I've also done a lot of things in the Technion and in the community, especially in the aspect-oriented community. I was editor of the Transactions on Aspect-Oriented Software Development, worked in an EU project. Within the department, I was very active in developing software engineering in the department, both in the lab and developing a degree program. And lately I've been active in the new cooperation between the Technion and Cornell in New York, designing new kinds of curriculum and sitting on all kinds of committees. Anyway, those have been interesting, but that's not really my research. My research agenda, all the way since I was a PhD student, has been to try and understand and master programming, just as many of the talks today have actually talked about that subject. So it's not surprising, because these are people that I've talked to, cooperated with, had common feelings that this is an important thing to try to do. I've done it mainly by either proposing different language constructs, but even more by using formal methods to try and conquer the complexity of software, to specify, analyze, and correct them. So it all started when I was a student became a PhD student at Weizmann Institute. The first course in master's and then PhD program in computer science in Israel in the early 1970s. People who came out of there included Nissim, who was a student with me, Nissim Francis, Alon Itai. Later, Nachman Dershowitz was also there. Quite a few other people working in different areas that populate computer science over the years in Israel. Anyway, the first subject that I worked on was on invariants. Invariants are things that don't vary. Invariant, that don't vary. And in particular, when you have a program and you have a loop, something that repeats itself, Dijkstra, one of the fathers of computer science, observed that the whole purpose of a loop, something that repeats, a piece of code that repeats itself again and again, is to take a step towards finishing, terminating, and while taking that step, reestablish an invariant assertion, some assertion that doesn't change. It's true every time the beginning of the loop is reached. And you can either have a loop and then try to figure out what the invariants are, or as Dijkra suggested, first think of the invariants and how you want to proceed towards termination, then write the loop based on that. So I went for the first direction. Zohar Mana, my advisor, posed this question. Okay, this is a great idea, but if you're given a program, someone's written a program, can we analyze it to figure out what those invariants are? Can we find the invariants? How can we find it? Just by looking at the code. Does it jump out? Is it something obvious? Well, we worked on this problem, which is undecidable, so we never could really solve it to the end. But we worked on it for years, and we have all kinds of interesting observations and results. This is a worthwhile activity, because even if the person who wrote the program wasn't thinking of the program, in order to understand what it's really doing and how it works, if you can find the invariants, that's a good step in the right direction. And this is true whether or not the program really is correct. It could be that he had a misconception. You can find out what those invariants, what those assertions were, and see what's the distance between this invariant, those invariants, and what you really want, and use that to correct the program, for example. So you can use invariants all sorts of ways. As I point out down here, you can use them for debugging and for program optimization, moving code out of loops, all sorts of other things. And so the question is, can you get them? So we did a lot of work in this. We coined the term logical analysis of programs. What was interesting was that I tried to run away from pure math that I had been studying it for my first degree and for 1 year at the Hebrew University, where you had all sorts of things like differential equations and all kinds of complicated things, partial differential equations. I didn't like it. And then I got into this stuff, and all of a sudden, the math started coming back. You know, you couldn't get away from it. So one of the ways to solve these invariants, like if you have a loop where you increase y by 2 in the loop, well, you can write that as what's called a difference equation, that the n plus 1th version of y is the nth version plus 2. And then if you know the initial value, you can then solve that using something called a generating function and see, oh, well, that y is actually equal to 2n plus 1 at the beginning of the loop, no matter how many times you go around. And I'm back with my mathematics, so that was very depressing. But anyway, that was just one way. And in other ways, we use heuristics. But the point of the matter is, again, I'm not going to go into the techniques that I use here, but these invariants were a crucial step in understanding how programs work, and that's a crucial step in making them work correctly. And so that was the overall goal. And you can use them for all sorts of things, including to try and show that the program really does finish at some point, even though, again, that's an undecidable problem. Some of the ideas we had there, we weren't able to implement because the technology wasn't there. I'm talking about the early 70s. Computers weren't fast enough, they didn't know how to do enough symbolic manipulation. So most of the things we did were abstract. 20 and 25 years later, different people reinvented some of the ideas independently because they weren't aware of some of this work, and implemented, and also, of course, they added new ideas. But this is also something that has been found useful by various people. Again, this is about the third or fourth time I'm showing you this picture that's been shown during the day. This is a picture of me sitting in the Sinai by my 155 millimeter artillery piece, writing a paper called A Closer Look at Termination. I've used this to inspire students to say, look, you think you've got all kinds of distractions? If you want to work on your research, you can blot out everything, sit down and work on the research. Don't give me any excuses that you're too busy, earning extra money or doing something else.
So Shmuel, the gun is the Terminator?
Termination is what happened to a lot of people, unfortunately, in that war. So anyway.
Did you consider adding audio effects to programming?
Yeah. Okay, so after I worked on that for some years, I turned to dealing with concurrency. And this is the period when I worked together with Nissim Francis on several important issues. Again, trying to conquer the complexity of concurrent programs. We came up, again, in that context with several